Okay. Perfect. There's a batch of students on their way, but I think to give you all the time, we should probably start now. Okay, so welcome everyone. Thanks for showing up. Really happy to host Ataberk Olgun. He's a senior PhD student in the Safari Research Group at ETH Zurich, and he's advised by Oner Mutlu. So very good group. His broad research interests include designing secure, high performance, and energy efficient memory and process in memory systems. His current research focuses on deeply understanding and efficiently mitigating the vulnerabilities caused by technology scaling in modern systems. His graduate work has been recognized by several honors, including induction into the HPCA Hall of Fame, which is extremely impressive to accomplish as a graduate student. So let's welcome the speaker and looking forward to the talk.
Thank you very much. And thanks for being here and spending the time. This is titled Experimentally Understanding and Efficiently Mitigating DRAM Read Disturbance. And this will be an overview of my research because of the limited time. But I'm happy to discuss the technical bits during the Q&A or even better after the talk. And I will refer you to many papers and many times to some of my papers throughout the presentation. And that's by design. And I only want to give an overview given the limited time. So this is a brief self-introduction. This is my contact information, and my research interests broadly include computer architecture, more specifically memory systems, making them better in many different terms. Today's talk is about memory isolation or lack thereof or in our systems. Memory isolation is a key property for system robustness. It states that a memory access to a memory location should not have unintended side effects on other or data stored in other addresses. If you access this memory location, for example, if you look at this picture on the left, let me just enable the pointer. Accessing this location should not randomly cause like a bit flip in some other location. Because if we allow that to happen, that can lead to data loss, that can compromise application correctness, leak private data, or can be used to take over computers. And this memory isolation property is difficult to satisfy in modern systems with DRAM chips because we use DRAM everywhere, and DRAM is fundamentally prone to read disturbance errors. And these errors can be used to break memory isolation. This picture will depict one such case of an error breaking memory isolation. It's a picture of tightly packed rows of DRAM cells. To access a cell in a row or to access a row, we must drive the word line to a very high voltage. And then to access another row, you need to close this. So you drive it to a very low voltage. And if you repeatedly do this, turns out you will induce bit flips in neighboring locations. And just some terminology, this repeatedly activated row, we call it the aggressor row, and the rows with bit flips, the victim rows. And this is a fundamental issue it's a widespread issue in modern memory chips, and all the chips you can buy today will be subject to these errors. Now, to understand rowhammer a bit better, we will look into DRAM charge leakage. Each DRAM cell encodes data in fundamentally leaky capacitors. And this is a simplified diagram of a DRAM cell, where the capacitor in red stores data as charge, and the access transistor sort of gates access to this data. There are a number of leakage paths by which charge can enter or exit the cell. And the key thing here is the stored data in the cell can become corrupted if too much charge leaks. This is going to show you how charge leakage happens over time. We see that capacitor voltage on the y-axis decreases over an exponential decay over time. And there's a Vmin, the threshold voltage, under which we can no longer guarantee that the cell will store the correct value. And to maintain the capacitor voltage above this value, we periodically refresh this DRAM cell. Now, if you look at this picture in the context of a rowhammer access pattern or a rowhammer attack, we can accelerate the charge leakage in the cell to a point of failure by hammering a nearby row. Now, if you look at what happens when the first refresh command or the first refresh operation arrives, sorry, there's like an animation bug here. At this point in time, the refresh sort of sees, quote unquote, the incorrect value in the cell and restores that back to the cell. So now the data in the cell has been corrupted. This paper from 2014 showed that row hammer bit flips were widespread and across many DRAM modules in 2014 again. And researchers from Google Project Zero showed that you can use these bit flips to take over systems by basically inducing targeted bit flips in your own process's page table. And once you have that sort of access to your own page table, you can gain access to the whole physical memory. Then a plethora of exploits emerge. You can do row hammer from a JavaScript code running on a browser. You can hammer your mobile phones. You can use GPUs or other system components to induce row hammer bit flips, because all you need really is a way to induce that access pattern in your main memory in the system. You can do row hammer using network packets. This is another example, using other components like FPGAs in these heterogeneous platforms. And this is interesting. You can use row hammer to leak secrets, because some bits only flip depending on what other data is stored neighboring this specific bit. So if you hammer a row and you see a bit flip in a cell you control, then you can infer what data was stored in the neighboring cells. You can use bit flips to significantly degrade machine learning model performance. This is another example. And you can use row hammer to infer average memory system power consumption and use that as a side channel. This paper in particular showed that error correcting codes that we use to basically maintain system robustness and basically correct random errors, they're not as effective as taught previously against row hammer, because you can induce more bit flips than what your ECC can correct. And you can induce these bit flips in a targeted way, especially if you can recover the error correcting code, encoding and decoding functions. You can also, so this is interesting, sometime around when DDR4 modules were released, the manufacturers claimed to have fixed row hammer. And this paper reverse engineered the manufacturer's undisclosed mitigation mechanisms or row hammer defense mechanisms and showed that you can bypass them and induce row hammer errors. There are many more interesting ideas that I won't cover in detail about row hammer. This is a survey paper from my advisor that covers updates until 2020. And we recently wrote a newer overview paper that covered more updates until 2023. I'm just flashing these here to let you know if you're interested, you could take a look at these. Row hammer did not stop in 2023. This work from Google broke the security guarantees of a row hammer defense proposed by Samsung Electronics researchers. And this is from 2024, showed bit flips in one DDR5 module. This is the most recent standard that you can find in contemporary computers, basically. And this work that builds on the previous one showed that you can reliably induce these bit flips in DDR5 modules. And finally, there are also bit flips in NVIDIA GPU DRAMs. This paper showed that for the first time. This happened very recently. On the other side, we also have new row hammer defenses being proposed. And this proposal from JEDEC is especially promising because this is like the first time the manufacturers have openly specified their row hammer defense technique. The basic idea is to count the number of activations each aggressor receives and preventively refresh victims before a bit flip can manifest in them. And this technique adds new DRAM cells to the DRAM array that their purpose is to just count the number of activations in the DRAM row. This is called per row activation counting. We analyze the security guarantees of it, and we see that it can provide security guarantees, provable security guarantees, at a row hammer threshold of 10, which we consider a very low threshold. Even 10 activations can induce a bit flip. But at that vulnerability level, the overheads of this technique is very high. It can hog DRAM throughput to a great extent. It cause up to 80% throughput loss. And we talk more about this in this paper. And then we proposed Kronos that aims to overcome the key inefficiencies of that mechanism. Finally, I think redisturbance is still a big problem, and more people are exploring more ideas to understand and fix the issues. And I strongly recommend people interested in Rowhammer to basically look at the DRAM security workshops that are collocated at ISCA. Yeah, and I believe there will be more research in this area because redisturbance bit flips happen in more DRAM cells with fewer activation counts as technology scaling continues. And this is a vulnerability that's difficult to defend against. And the good thing is, this gives us, like architects, more things to do. And I'm going to describe the solutions to redisturbance issues and new experimental studies that deepen our understanding of the phenomenon in this talk today. So I'll continue with variable redisturbance. This is an experimental analysis of temporal variation in DRAM redisturbance. This is a typical DRAM-based computing system with a CPU and a DRAM module. And the DRAM module has many chips. Inside the chip, you have many banks that share the same interface. And inside each bank, you have many subarrays. Inside the subarray, you have the two-dimensional array of DRAM cells laid out onto word lines and bit lines. Now, to access data in a DRAM row, that's the red rectangle here, you need to activate that row. And many repeated activations can lead to Rowhammer bit flips, as we discussed before. But there's also row press. Row press induces bit flips by keeping the aggressor row open for a very long time without needing to repeatedly activate the row many times. And we will talk about row press a little bit more a little later. Many different prior works proposed a variety of defense techniques that aim to prevent Rowhammer bit flips. They offer a different point in the area, performance, and security trade-off space. But a common operation pattern across all of these is that they need to take an action before a bit flip can manifest in a victim row. And to do so, they must accurately quantify the amount of redisturbance that a victim row can withstand. And this is typically quantified by testing for redisturbance failures, time-intensive testing, because no manufacturer publishes what redisturbance vulnerability their chips have. So you have to figure this out yourself. And typically, we use the redisturbance threshold. That's the number of aggressor row activations needed to induce the first bit flip as a metric to quantify the vulnerability, the redisturbance vulnerability of a row. I'll try to illustrate why it's important to accurately identify the redisturbance threshold. The x-axis here shows increasing RDT values in arbitrary units. And the y-axis is the performance overhead and energy overhead of your defense mechanism, again, in arbitrary units. So this is what you would expect to see. It's a sketch. It's not a real, this is not real data. Because your performance and energy overheads increase with reducing thresholds because you take more preventive actions more frequently, and each preventive action induces some latency overhead and energy overhead. If you have this ground truth value for RDT, then you want to configure your defense mechanism with that value exactly. Because if you can configure it with something higher, then you won't have the guarantee that you will be able to prevent the bit flip at the right time. So this is an insecure mechanism now. If you configure it with something very low, then you're inducing a lot of unnecessary refresh operations, unnecessary preventive actions, and each of them induce some significant overhead. That's the thing, basically, to securely prevent bit flips at low performance and energy overheads, we must accurately identify the redisturbance threshold. Yes, so this work tries to answer the key question: how accurately and efficiently can we identify the redisturbance threshold? And with more than 100 million redisturbance threshold measurements across thousands of rows and many important test parameters, we show that the redisturbance threshold of a row changes significantly and unpredictably over time. The minimum observed redisturbance threshold for a row can be 3.5 times smaller than the maximum observed for the same row across time. And the smallest value for a row can appear after tens of thousands of measurements. And these have significant implications for system security and robustness because we show that you cannot identify redisturbance threshold accurately and easily. And given our limited data set of bit flips, we evaluate a short-term solution whereby we use guard bands. We guard band a redistribution threshold value observed using a few measurements. So you test your chip for 5 times. You find the minimum value, you apply guard band of 10%, and you use contemporary ECC. We see that that may prevent redisturbance bit flips induced by VRD, but these numbers can only get worse. So I would like you to keep that in mind. With more data and more analyses, the guard bands you will need can only increase, and the ECC strength you will need can only also increase. And our work calls for future work and better understanding and efficiently mitigating VRD. To achieve the goals we set out to achieve in this work, we experimentally characterized DRAM chips using the DRAM vendor testing infrastructure, and you see a picture of that infrastructure here. We have an FPGA board that implements our specialized DRAM testing logic. We have the DRAM module that you cannot see, it's hidden behind this heater setup that's controlled by a temperature controller. This setup allows us or enables us to have fine-grained control over DRAM command sequences that we create and temperature. And this is a different version that we use to test high bandwidth memory chips. I'll take a little of time to introduce this infrastructure to you. It's called DRAM Vendor, an extensible and versatile FPGA-based infrastructure to easily test state-of-the-art DRAM chips. There are many factors that affect DRAM reliability and latency, and these cannot be properly modeled or easily modeled or analytically or using simulations. Therefore, we need to perform experimental studies of real DRAM chips. And open source DRAM testing infrastructures allow us to do these experiments. However, they have several limitations that make them difficult to use as flexible, accessible, and extensible platforms. And DRAM Vendor's goal is to overcome those limitations, and we provide many, so we open source DRAM Vendor, and we provide many different FPGA-based prototypes that you can that's readily available for you to use today. In the paper we published on DRAM Vendor, we showcased 3 case studies just to show you the types of experiments that you can do. Of course, we can study redisturbance with this infrastructure, but we can also do interesting stuff like bitwise majority across DRAM cells laid out onto the same bitline. If you open 3 DRAM rows at the same time, you can realize the bitwise majority operation across those 3 rows. And that leads to some very interesting computational capability in real DRAM chips that you can buy today. Yeah, there are more details in the paper that I won't be able to cover. But I'm proud to see that DRAM Vendor enabled a lot of research. I'll be covering a few of them today from our group and from other research groups. And one highlight I'll briefly cover is row press. We've seen that repeatedly activating a row induces bit flips, and row press shows that keeping a DRAM row open for a very long time is also enough to induce redisturbance errors. And in an extreme case where you keep a row open for 32 milliseconds, this is an extreme case because the standard specification does not allow you to keep a row open for that long. But if you do, you can get bit flips with a single activate command. In the average case, you see an 8 to 9 times reduction in the number of activation count. If you use a row open time of 7.8 microseconds, this is the distance between your refresh commands, compared to when you use 36 nanoseconds of row open time, which is the minimum that you can do specified by the standard. We have more results in the row press paper, and our work is fully open sourced and artifact validated. So that's what DRAM Vendor allows you to do. And I'll go back to variable redisturbance now. These are the DRAM chips we tested for this work. We test various dynasty divisions and chip organizations to cover like a variety of chip designs. And we carefully use the rigorous redisturbance testing methodology where we eliminate sources of interference like refresh, redisturbance mechanism, error correction codes to see the device level bit full of distributions properly. And we use the worst case redisturbance access sequence whereby we hammer or repeatedly activate 2 aggressor rows, physically sandwiching a victim row, and we record the bit flips observed in this victim row. When I say one hammer, what I mean is we open and close both of these aggressor rows once. So 2 activations mean 1 hammer operation. I will introduce you to the foundational results we present in the paper, and I'll move on to the other work. But this is the key observation that I'd like you to take away from this part of the presentation, if possible. We find that the redisturbance threshold of a DRAM row changes randomly and unpredictably over time, and that makes accurately identifying the redisturbance threshold very challenging, and it has all sorts of security implications that I described earlier. Here we will plot the redisturbance threshold values observed across many redisturbance measurements or samples for a single DRAM row. And this is an example point that yields an RDT of around 37,000. These are the first five measurements for the row. This is the first 1,000 measurements. And we compress those 1,000 measurements to this shape where the circle shows you the average and the ends of the bar show you the maximum and minimum across 1,000 measurements. This is across 100,000 measurements. For this specific row, we observed the minimum value at around the 17,000th measurement. And this is a key result that demonstrates the variable redisturbance phenomenon. Of course, we have data from other rows and other chips. This is to show that the redisturbance threshold of a row has multiple states. You see a histogram of redisturbance threshold values on the x-axis. And this is for a single chip. I'll show you what we have for 6 chips. For like more chips and more data, I will have to refer you to the paper. We also analyzed the predictability of the next RDT value given a past RDT measurements, and we find that it's likely unpredictable. The reason why we think it's unpredictable is because these histograms that I showed you earlier, they well resemble random probability distributions, such as the normal distribution, and this kind of hints to us that maybe there's a physical random process that's driving these results. And the second thing is we use the autocorrelation function to try and identify repeating patterns in a series of 100,000 measurements, and we cannot identify any repeating patterns. That's why we say VRD is likely unpredictable. And for more details on our methodology, I have to refer you to the paper. We also have an in-depth analysis of VRD in the paper that I won't cover in the given the time limitation. But I'll talk about the implications this poses a little bit. It has serious implications for system security because your solutions, your redisturbance solutions, rely on an accurately identified value. And our results show that accurately identifying that redisturbance threshold value is challenging. And we evaluate a short-term solution that's used guardbands and ECC, and we show that guardband and ECC may prevent bit flips, but you need more data to make a conclusive statement about the effectiveness of those techniques. And there are many more things in the paper that I cannot talk about today, but I'll be happy to dive deeper into VRD. And I'll momentarily stop to take questions if you have any. All right. If not, I'll continue. And if you have any questions, you can also stop me, by the way. I'm okay with that. All right.
You want online?
Okay. Yeah, that's it for VRD. Prior to VRD, we also looked at redisturbance in detail in high bandwidth memory chips. We knew that many DRAM chips of various form factors were subject to redisturbance, and we were curious to see how it looked like in high bandwidth memory chips. And we thought it's important because high bandwidth memory chips are extensively used in important system infrastructures of today. And for example, several popular machine learning applications of today rely on high bandwidth memory. A typical high bandwidth memory system looks like this. You have a compute chip that can be an FPGA, GPU, etc., and one or multiple memory chips or memory stacks. And those are your high bandwidth memory DRAMs. These are integrated into a single package to form the HBM system. And this is a different view of the same system. All I'm going to say is that the unique thing about the DRAM stack here is that there are multiple DRAM dies stacked on top of each other. And you have independent channels that you can access from your FPGA and GPU through the HBM interface. If you look inside the channel, you will see the picture I showed you earlier, so I won't talk about this in detail. And we use the DRAM testing infrastructure to perform this study, and I showed you this earlier too. The testing methodology is very similar, and the differences are not worth mentioning given the short time. The two metrics we look at in this study is the bit error rate. This is the fraction of DRAM cells in a row that exhibit bit flips with 256,000 hammers. And the higher this gets, the worse it is for that DRAM row because you have more bit flips. And the second thing is the redisturbance threshold, but it has different names. Here we use the hammer count to the first bit flip name, HC first. This is the same as the redisturbance threshold. So a lower value will mean that you need fewer activations to induce the first bit flips, which means it's worse for that row. We looked at how row hammer spatially varies across the HBM stack because you have this 3D stack structure. That's one of the most interesting things to look at. And here, this figure depicts you the distribution of bit error rate across rows. In each box shows you the distribution across the distribution of bit error rate across rows we tested in different channels, different 3D stack channels. Here, we see that there are bit flips in every tested row and every tested channel. So HBM2 is not, as expected, it is vulnerable to redisturbance. And the second observation here is that bit error rate varies across channels, and you can identify groups of two channels that have, within the group, have very similar bit error rate profiles. If you look at channel 3 and 4, they are very similar to each other. The distribution is very similar to each other, and you can match every channel with another channel by looking at the profile, the distribution profile. Why I'm stressing this is because we think this could indicate that these channels reside on the same DRAM die, even though we cannot confirm this with information that's publicly available. And this is showing you data on more data patterns. I'm going to skip this because it's not very interesting. I'll talk about the redisturbance threshold or HC first. We see that the lowest HC first across all the rows we tested is around 14,000, which yields about 1.3 milliseconds of hammering needed to induce the first bit flip. And it heavily depends on what sort of data patterns you initialize your DRAM rows with. And we look at the redisturbance sensitivity to row on time. This is the row press study, basically. And we see that row press is also prevalent in the HBM2 chips we tested. With a higher aggressor row on time, that means you keep the row open for longer, your bit error rate increases. And the more you keep a row open, the longer you keep a row open, the fewer activations you need to induce the first bit flip. And in an extreme case, we see that a single hammer is enough to induce the bit flip if you keep the row open for 16 milliseconds. These observations have important implications for redisturbance attacks and mitigations. So for an attacker, if the attacker could figure out which channel is the most vulnerable channel, they can focus their attack there. They can, because a bit flip typically will induce some sort of error correction. So if you induce a bit flip, you will induce an error correction if there's a single bit flip that ECC can correct. That will be registered like as a correction. And if you see many error corrections happening, there's a chance that as the system designer or the system maintainer, you will think that something is wrong with this chip and file an RMA for it, right? So these bit flips are very important to mitigate, not just because they are a security vulnerability, but it is more than that. It's a safety and reliability issue in its essence. And for mitigations, you could, in theory, allocate more resources to defend the more redisturbance vulnerable channels and allocate fewer resources to defend the less susceptible channels. And I won't go into the details of how, but those are the implications we think these observations have.
But what are folks actually doing to differentiate between an actual like a error-prone chip or a DRAM?
That's a good question. I think that needs a lot of manual effort in trying to figure out what caused that error to begin with. So you'll be looking at error logs. You could make an educated guess if you have very detailed error logs. But someone needs to first have to allocate the resources to and consider this a problem first, and then allocate the resources to figure out what is differentiate between row hammer errors and other sort of errors, and then someone has to analyze these, I believe.
And sorry if you said this, but are there persistent effects of row hammer, or is it always transient?
That's
if I keep hammering, do I eventually get a bad chip, or?
Bad chip as in, it's like a hard error, like stuck.
Yeah.
Okay.
Or I eventually degrade the performance of that cell to where I end up.
I see.
Even in non-row hammer, things get the fault.
Yeah, I have not seen that happen in my experiment. So it's mostly transient. As in, if you could refresh it in time, you wouldn't see the error. If you could refresh the victim in time. Yeah. I'll be skipping this part. I'll talk about one more thing we did in the study, but very briefly. The HBM2 standard, if you look at it, there's a target row refresh mode whereby the memory controller and the DRAM, they cooperate to prevent row hammer bit flips. So the key idea is the memory controller periodically sends some specialized refresh commands for row hammer mitigations. We're not looking at this because there were on-die mitigation mechanisms implemented in DDR4 chips. Those came earlier than in 2. These were not specified in the standard at all. These were memory controller transparent. They took actions hidden behind the periodic refresh operations. We queried the existence of those sort of on-die mitigation mechanisms. And we found that it does exist. And I'll show you just the key details, not the details, but the key idea. We identify that there is an undisclosed on-DRAM die mitigation mechanism. It takes an action every 17 periodic refresh operations and refreshes both of the adjacent rows. So if you hammer an aggressor row, the victims on either side will be refreshed by this mechanism. And it has a very interesting way to identify what is an aggressor row. The key thing is it's not perfect. So you can come up with a specialized access pattern and convince the on-die mitigation that you're hammering, these bunch of dummy rows that you're actually not hammering. So it keeps refreshing your dummy rows, but you accumulate the activation count for a few select set of rows that those are your real aggressor rows, and you can get by without having your victims refreshed and induce bit flips. And that's what we show in the paper, along with many other things. But yeah, again, I will be skipping these details in the interest of time. So those are the experimental characterization work that we did to understand row hammer and redisturbance in general better. Now I'll be moving on to defense mechanisms, but before then I'll stop again to take questions. Okay. Bonzu. Oh, then I'll continue. So as I said, I'll publish. Excuse me?
Where is this? I see archive. Is this?
Oh yeah, this was published in DSN 2024.
Okay.
Yeah, switching gears, moving on to defenses. So this is called Abacus, all bank activation counters for scalable and low overhead row hammer mitigation. Hopefully you're convinced that row hammer is getting worse. And you remember that there are many ways to mitigate row hammer bit flips, but we're focusing on preventive refresh based ones because they're generally more resource efficient and lower overhead than other approaches. The key idea of preventive refresh is to refresh the victim rows of an row hammer attack before bit flips can manifest in those rows. But to do so, you need a way to track the activation count of your aggressor rows. And if you look at the prior work, when we when we started working on Abacus. No existing mechanism prevented rowhammer bit flips at low area, performance, and energy costs at the same time. And our goal was to provide that mechanism, especially at very low rowhammer thresholds, back then, which we considered to be around 125 activations. Abacus's key idea, which I'll talk about in the next slides, is based on this key observation that we make on how common workloads interact with main memory. And I will show you this over an example. And this is a system with a CPU and 4 DRAM banks, and each DRAM bank has a DRAM row at row address row X. And this is a DRAM row with the same idea across different banks. Now, a workload running on the CPU will create a bunch of load requests, and the way the CPU executes them will be like this. So first you access bank 0 row X, then you access bank 1 row X, and you might access some other row in any of the banks, but the general trend continues, and you have basically issued a load request to row X in all of the banks. We call these rows sibling rows, and I'll explain why this sort of access pattern is prevalent across many workloads. First, there's inherent special locality in memory accesses of a workload. A program usually tends to access neighboring cache blocks at around the same time. And you can imagine streaming access to an array to create this sort of access pattern. And this important thing is the modern physical to DRAM address mappings we use, they distribute neighboring cache blocks to different bank groups or banks, but into the same row. And they do this because only you will get the highest DRAM throughput or the advertised DRAM throughput only if you interleave read accesses between different banks or different bank groups. And we back this observation up with real workload simulation studies in the paper, but I won't be talking about these in detail. I'll talk a bit about existing solutions. Existing per bank activation counter-based mitigation mechanisms have an important issue. There are many banks in a DRAM chip, and the number of banks and thereby the number of activation counters increase with newer DRAM generations. And we have seen that sibling rows have similar activation counts. And our key idea is quite simple, is to use one activation counter to track the activation count of all sibling rows. And thereby we can reduce the number of counters by a factor of the number of banks in the system. Now, our objective is to keep track of the maximum activation count across all sibling rows using one counter. And pictorially depicting that is basically, if you have this sort of state in our counters across banks, Abacus-based counter should have a value equal to or larger than this -7, this bank 15's activation count. Because if you keep a value that's smaller than this, then you cannot preventively refresh on time. You might induce bit flips. And if you maintain a value that's much larger than that, then that will lead to unnecessary preventive refreshes and high overheads. So our design goal is to keep the counter value as close to the maximum activation count as possible. And in the paper, we describe how we do that. In this talk, I won't. Again, if you have questions, I'll be happy to answer them. We use a cycle level memory system simulator to evaluate Abacus. And this is our system configuration. And we compare Abacus to 4 state-of-the-art rowhammer mitigations. These are namely Graphene, Hydra, Rega, and Para. Graphene is the best performing one. Rega and Para are the lowest processor chip area cost inducing mechanisms. And Hydra is somewhere in between in both performance and area cost.
What does the industry care the most about?
In terms of like these
Performance or area?
Both. Unfortunately. I mean, it is a trade-off. Yeah. They have opted for a mechanism that induces some performance overhead at, well, almost zero cost processing area. This is the per row activation counter mechanism standardized in JEDEC, standardized by JEDEC in DDR5. The idea is to put activation counters inside the DRAM chip as DRAM cells. and that induces some design changes to the DRAM chips, which is deemed costly, but they were willing to take on the cost. It comes with a significant latency overhead. Your key DRAM access latencies increase by around 10%. That leads to performance overheads, and we show that in the paper that where we evaluated this mechanism. So there's some performance overhead and no area overhead from the perspective of the system design, because the DRAM chip is taking on the cost. Yeah, this is standardized, but as far as we know, no chip implements this yet. So it's like an optional feature in the DDR5 standard. It is a bit weird, and the plan, as I've heard, is to standardize it in DDR6 as like a not an optional but a required feature.
So most RAM doesn't have this now, but the DDR6 standard they will.
I think so, yes. Yeah. So DDR6 will have is the general consensus. But because it's not the most inefficient way of dealing with the problem, I hope there will be more work that solves the issues of track. And let's see what happens. Yeah. And we use many workloads to evaluate the performance of Abacus and the other mechanisms. This is single core performance and energy results. At a very low programmer threshold of 125, the average performance overhead we observe compared to a system with no mitigation is 1.5%, and the DRAM energy overhead is 1.2%. And that allows me to claim that Abacus prevents bit flips with very low performance and energy overheads. You compare Abacus to other mitigation mechanisms. This is 8-core multi-program performance results. It's very crowded, but the key is Abacus outperforms Hydra and Para at all row hammer thresholds on average across all workloads, and it performs very close to graphene, and it has some overhead compared to graphene because there are unnecessary preventive replay operations that Abacus does because it uses a low-cost aggressor row activation tracking scheme. So that's the area performance trade-off. This is the same plot, but for DRAM energy, we observe that Abacus consumes less energy than Hydra, Rega, and Para at the tested row hammer threshold smaller than 1000. And Abacus performs similarly to graphene in terms of DRAM energy, and that's only 4% higher than graphene at the very low row hammer threshold value. We also evaluate Abacus's area overheads and show that it's comparable to Hydra and it's much lower than graphene. Then we have more results in the paper that I won't be going into. And this is also open sourced and abstract evaluated. That's Abacus. I will now talk about self-managing DRAM, but again, you can stop me to ask questions at any point. I see no questions, so I'll continue. This is a low-cost framework for enabling autonomous and efficient DRAM maintenance operations. Let's see at a high level what the DRAM interface looks like today. The DRAM chip communicates with the memory controller over the DDRX interface, where the memory controller sends DRAM commands. It orchestrates all DRAM operations by issuing DRAM commands, and the DRAM chip executes all DRAM commands without any question. And therefore, we say that the DRAM interface is completely controlled by one side. And while controlling DRAM, the memory controller issues DRAM maintenance operations. And it does this because DRAM is subject to many error modes, such as the ones that I show you here. And these maintenance mechanisms will maintain data integrity. That's why they're important. And one prominent example is periodic refresh. Now, as manufacturers scale storage densities, the error modes cause more errors. And the key point I want to make here is that continued process scaling will necessitate new efficient maintenance mechanisms. And these mechanisms are defined as part of the JEDEC, the DRAM standard. The standard is proposed by JEDEC, which is composed of more than 300 companies. They define the standard and then produce devices that obey the standard. And we think that the DRAM standard poses a barrier to entry for new efficient mechanisms, because if you want to add a new mechanism or modify an existing one, you have to change the DRAM standard as well. And the key reason for the barrier to entry is that the DRAM interface is rigid. It is also not easy to release a new DRAM specification, because doing so requires a multi-year effort by a huge committee. And this also makes introducing new maintenance operations take a very long time. It's not that you will need 5 years or 8 years to design a new maintenance mechanism. It might take you 2 minutes if you're very good, but you have to wait for the specification to be released until people can enjoy the benefits of new mechanisms, such as the ones that DDR5 introduced. Those are 3 different techniques that we identified that improve performance, robustness, and error tolerance. And if these improvements could be released earlier, or if the standard, if we didn't require changes to the standard, these improvements could be released earlier as well. So the problem is that introducing new maintenance operations take a very long time. And our goal is to ease and accelerate the process of implementing these operations. Now, before I explain your solution approach, I'll categorize DRAM operations into 2 classes. The first class will be access, and the second one will be maintenance. Access operations are performed to serve memory requests. Those are like reads and write operations. And we need information that's available only to the memory controller, such as the load address and the stored data. But for maintenance operations that we do to maintain data integrity, we typically use information available only to the DRAM chip. We don't really need information available to the memory controller. And here you could observe that the DRAM chip could maintain itself because it has all the data it needs. And a DRAM chip should maintain itself because of 2 other reasons. The first one is the one that we already covered. You can implement maintenance mechanisms more easily and possibly faster, because doing so does not require any changes in the DRAM interface. And the second is it enables DRAM manufacturers with some breathing room to perform architectural optimizations without exposing DRAM internal proprietary information to other parties through discussions they might have in the JEDEC committee meetings. And our solution approach is to enable autonomous maintenance operations in DRAM chips. However, the DRAM interface definition is too rigid to accommodate an autonomous in DRAM maintenance operation in real DRAM chips. In particular, the DRAM interface is designed in a way that yields all control to the processor. And our goal is to make a simple change to the DRAM interface and enable autonomous maintenance operations. Another way to look at this is we're moving to the right on this DRAM interface design scale, where we're giving some more breathing room to DRAM manufacturers to improve their DRAM chips without having to discuss a lot of proprietary details. And to that end, we develop self-managing DRAM. The key idea is to enable autonomous DRAM maintenance operations, and doing so introduces a new problem that is what we call access maintenance conflicts. If your DRAM chip decides to start maintenance on a region or a bank of inside the DRAM chip, and the memory controller decides to access that specific location, there will be a access maintenance conflict. And our proposal to avoid this is to add a single signal, that's the negative acknowledgement signal, that the DRAM chip selectively uses to reject only some of the activate commands that the DRAM controller sends. And in summary, SMD enables autonomous in-DRAM maintenance operations with a simple change in the interface, and divides the work nicely between the memory controller and the DRAM chip, such that new maintenance mechanisms can be implemented without modifying the standard. Now, that is the key idea, and I am satisfied with that much information given across. And I'm running out of time, so I will probably spend the rest of the talk for the time for questions.
How involved are you in the JEDEC standards meeting?
I am personally not involved at all.
How does it, like I know there's been some, for example, ISCA papers that made their way into the branch standards and influence them. Do they read your papers and obviously they read your and your lab's papers?
I believe so.
That goes into the decision make? It's a company conglomerate? How's it work?
Right, so it's basically everyone involved, every stakeholder and anything related to DRAM. So Microsoft would be there, Google would be there, DRAM manufacturers would be there. I believe they're reading our papers. I'd like to believe that. And I'd like to believe that we are making an impact on the decisions. But I personally am not involved.
But they have meetings or there's
Yeah.
like, it's like
They
there's like
create,
specs, right? So they like put out provisional specs and everyone can read them and give feedback.
I don't know exactly how the meetings go, but they created a task force for Rowhammer specifically. Dated, I don't know when, 2010s. So there is a task force on Rowhammer specifically that continues to deal with.
So is there like a chapter of the standard that's on Rowhammer?
Now, yes, and DDR5, yes. And maybe other new standards also, yes. But in the past, it was not acknowledged.
Is that the most serious reliability, security issue with DRAM? Rowhammer?
Security issue, maybe yes, because these are like induced targeted bit flips that, you can even control the direction of the bit flip. And you can do that and even if your memory controller obeys the standard specification, even in DDR5 chips today, which have the most recent, most powerful defenses, as the Phoenix paper shows well, it will be published next year in IEEE SMP, but it's already uploaded to archive. So I would say it's one of the most important. The only one I know that allows you to induce bit flips in a targeted way. Yeah.
I have a question about Abacus if you have time.
Yeah, sure.
Could you go back to the slide with the pictures of the Abacus counter? Yeah, this one. So if I understand correctly, what you're trying to do is you want to, based on the activation count, you want to have that sweet spot of when you do a refresh. So if you do it, you're saying if you have too low of a count, then your refresh happens too infrequently, and if your count's too high, then you're too aggressive. Is that a fair statement?
If your count is too aggressive, then you're not doing the refresh at the right time, so that could lead to a bit full.
Yeah. So then you need a max tracker based on.
Right.
So I know you mentioned you didn't have enough time to talk
Yeah.
about it, but could you elaborate on how the counter works?
Right. So unfortunately, I don't have the best slides to explain this, but basically, you still need to maintain some additional state. So you cannot do it just one counter.
Yeah.
What we have is a bit vector, 1 bit for each bank. Imagine you have 4 banks or 2 banks. Yeah. And a count instead of having 2 counters for each bank. So you still reduce the area cost a lot as your banks increase. That's the area saving benefit. But the way the algorithm works is you activate row 0, let's say, in bank 0. That increments your counter and sets the bit vector for the bank 0 to 1. Now that kind of indicates that since the counter was last updated, this bank was activated once. If you open the other row in the other bank, you don't need to increment the counter because the bit vector will just switch to 1. The counter does not need to be incremented. If you open a row and the bit vector is already a set bit, that means you need to increment the counter and reset the bit vectors. So it's like
Every bank gets an opportunity to
right.
increment 1 per count on the shared
Yes.
count.
And you can already guess what happens when you only activate a single row, right? Or you literally activate a single bank, then the counter keeps getting updated. And if you have that sort of an access pattern, what ends up happening is only one bank is being hammered, but you need to refresh all the rows. That's the worst case for Abacus, but we see that doesn't happen in the common case.
I see. And so the overhead is, or like what you recommend is a dedicated, you said dedicated cells within the DRAM chip.
So one thing I didn't mention is that this is like a memory controller based mechanism, so you wouldn't modify DRAM at all for this ideally. And within a DRAM chip, yes, there are like other mechanisms that. So you need one counter per row across all banks, plus as many bits as the number of banks you have.
Space optimization. 经典 follow up space optimization.
So great.
Yeah, very impressive. Lots of work, very rigorous. So let's thank the speaker. And then you can have some time to chat with the students more later. And for now, maybe we can also stop the recording.
Yes.